Hello, this is Jack Jackson. Today we're going to be looking at the cosine angle sum identity here. So the cosine angle sum identity says that cosine of angle A plus B is equal to cosine of A plus cosine of B. No, say that again. Cosine of A plus B equals cosine of A times cosine of B minus sine of A times sine of B. And so we want to prove this identity. We're going to be using my sketch Trigonometry Ultimate, and the page we're on is called Cosine Angle Sum Identity, which is this page. So here goes the proof. We start with the coordinate system. Let O be the origin. Let J be the point 1, 0 right here, and we're going to construct the unit circle. So the unit circle is going to go through point J at 1, 0. Let F be the point on a angle that has measure A. So put A in standard position, and so A is going to be an angle something like this. Could be anywhere. Okay, and we can measure it the way I've got this one marked. I'm measuring either in the positive direction for the first and second quadrant, third and fourth for the terminal side. I'm measuring in the negative direction. But let's say we have some angle A here, and F will be the coordinates where that terminal side meets the unit circle, and of course by definition that'll have coordinates cosine A, comma sine of A. Now let's put an angle B in standard position also. Okay, and here's angle B. And again, I can make B, doesn't matter, I can make B larger than A or smaller than A. There's larger or smaller, but B has some measure there. And let's say B goes to this point, E. E is going to have coordinates cosine B, sine B. Now the next thing I want to do is I want to look at the angle minus B. Okay, so however far I go out E, I'm going to go the opposite direction for minus B. So let's go, for example, right here. And of course that will be cosine, well, it's cosine of minus B, sine of minus B. But remember that by some trig identities that we have, even odd identities, cosine of minus B equals cosine of B, and sine of minus B equals minus sine of B. Okay. So let me just correct a couple things here. So this also equals cosine of minus B, comma, sine of minus B. Okay, and I've used a even odd identity. Okay, so we have that point. Now, we are going to, now we want to find A plus B. Okay, so now A plus B, we have to notice that we've rotated around from this point J, A to here, and we need to rotate an additional amount by B. Okay, so here's the angle here with the purple terminal side. So notice as I let B be 0, that's the same as A, and as I rotate this B a little bit more, however big I've made the angle B, that's how far we've gone from A, an additional amount. Or likewise, however far A is, that's how much additional we've gone from B to get to this point. Okay. So that point is going to have cosine of A plus B, comma, sine of A plus B for its coordinates. Okay? And the coordinates for each of the points follow directly from the unit circle definitions of sine and cosine, and the simplifications we made for point G were from the even and odd identities. Now, the next thing to notice is that all of these segments that go from O out to the circle have length 1. So those are all congruent segments. So in particular, O to F, O to H, O to H here, O to F, O to E, and O to G are all congruent, namely 1 length. Okay, now what we're going to do is we're going to make a couple of triangles here. And we're going to connect up these points here. So we're going to connect up point F and J, and that's going to make a triangle going F to O to J. Now we know that's an isosceles triangle. Then we're going to have another triangle going from connecting up F to G, so that we have another isosceles triangle going F to O to G, FOG. And so we have two triangles. And here are the interiors of those triangles. Okay. Now, I am going to claim that these two triangles are congruent. Okay. How can we prove that they're congruent? Well, we already have two pairs of corresponding sides. This side right here, on the purple side here from O to F, is congruent to the corresponding side here from O to F is the green one, and then the I believe this point is H. Yeah, H here. So O to H and O to F are congruent, and then likewise down here, O to G is congruent to O to J. So those are all congruent. In fact, they're all congruent to each other. Now, what we're going to do is show that the angle in the middle is congruent too. So the angle between them, well, what does it measure? Well, this one goes out A, and then you add another B to it, so this angle is A plus B. The angle from J to O to H is A plus B. And similarly, the angle here is, well, if we go this direction, it's B. If we go this direction, it's minus B. But if we go this direction here, it's B plus A. So this is B plus A, or A plus B, for the angle going from G to O to A, or F there. And so we get A plus B for both of those angles there. Well, that makes the two triangles congruent by the side angle side postulate. Now, since they're congruent, that means the hypotenuse hypoteni of the two triangles are congruent. So these two green lines segments are congruent, the darker one and the lighter one here. So from H to J is congruent to from F to G, because corresponding parts of congruent triangles are congruent. Now we're going to get to some algebra. We also know that we have coordinates for all of these points. Okay, so this coordinate for F is here. Here's the coordinate for H. Here's the coordinate for E and G. And so we can use the distance formula to compute these distances, and we know that they have to be equal to each other. So we've got several steps of algebra to work through here. And so here we have the reasons over here on the right. Well, first of all, we know corresponding parts of congruent triangles are congruent. This is CPCTC. That's short for that. Corresponding parts of congruent triangles are congruent. So by that we know that the distance from F to G is equal to the distance from H to J, which is what this is saying. Now we just use the it's the Pythagorean theorem, which gives us the distance formula. So we're going to use the distance formula. So distance formula says is the distance between 2 points, remember, is the square root of delta x squared plus delta y squared. So we're going to take the difference in the x coordinates. So we're going to take cosine B minus the cosine of A and square it for the difference in the from F to G. So we're going to find this distance of this green one right here. So we take its x coordinate of the G minus the x coordinate of the F and square it, plus do the same thing for the y's. The y coordinate of the g minus sine of b minus the y coordinate up here of the f and square it. So that's the distance on the left side. We add we do those subtractions to find delta x and delta y, then we square, then we add, then we square root. On the right side, we want to find this other distance of this lighter green one here from h to j. So we do 1, again we subtract the x's to find delta x. So it's 1 minus cosine a plus b, and we're going to square that, plus, and then we do 0 minus the sine of a plus b, and square that, add them up, square root. So the distance formula gives you those two formulas. Okay, let me get that out of our way. Alright, now let's just work with the algebra down here for a minute. Well, the first thing I want to do is square both sides. And so we get cosine of b minus cosine of a squared plus negative sine b minus sine a squared equals, and the other side, parentheses 1 minus cosine of a plus b quantity squared plus 0 minus sine of a plus b quantity squared. Notice that we have just basically canceled out the square roots by squaring both sides. We can do that. Next, we expand out these squares. Now let's just remember just a minute about squaring something. In general, if you have, say, x plus y and we want to square it, of course that's x plus y times x plus y. And if we multiply that out, y times y is y squared, y times xy is xy, x times y is xy, or x times x is x squared. Add together, you get a y squared. The middle terms double up, 2xy. Or you can think of that, the shortcut FOIL. First times first is x squared. The outer product is xy. That's the O. F-O-I-L. Inner is x times y, which is xy. And last times last is y squared. And so we get x squared plus 2xy plus y squared. So when you're squaring something, the shortcut is square the first, square the last, multiply them together, and double it for the middle. So that's squaring a binomial. Remember that from our beginning algebra classes. So we're going to use that property right here. So we square the first, cosine square of b. We square the last, plus cosine square of a. And then we multiply and double it. That's minus 2 cosine a cosine b. Now we're going to do the same thing here. We're going to do this several times. So here we square the first. The two minuses make positive, so that's sine square of b. We square the last. Two negatives squared make positive, so that's positive sine square of a there. And we multiply. Two negatives make positive. Multiply and double it to the middle, so that's 2 sine a sine b. And then that's all added together on the left. On the right, we can do this again. 1 square is 1. We got minus cosine of a plus b squared is cosine square a plus b right here. And we multiply and double it, that makes minus 2 cosine a plus b. 0 minus this is just negative sine of a plus b. We square it, the negative, two negatives make positive, and this is sine square a plus b. So we're just expanding those binomials out using FOIL, which is really just the distributive property. Okay, now we're going to do a little reordering, okay? So cosine square of b is of a, where's that one? That's right here. We're going to put it first, and then we're going to put sine square of b with it, which comes from right here. Here's sine square of b, cosine square of b, cosine square of a is here, cosine square of b is here. Sine square of a is here, sine square of b is here. Here we're going to get what's left. We already got that one. We need this one, minus 2 cosine a cosine b, we put that here, and plus 2 sine a sine b, put that here. Alright. That is not grouped the right way. Let me fix that. This is supposed to be cosine square A and sine square A. This guy is supposed to be grouped with that one. And this one is supposed to be grouped with this one. There we go. Now why do I want to do that? Well, because in the next thing we're going to use our Pythagorean identity. It says if these have the same inputs here, cosine square of something plus sine square of the same something is 1. So cosine square of A plus sine square of A is 1. Cosine square of B plus sine square of B is also 1. So we've got to get the grouping right there. And so those simplify quite a bit by putting those together. Okay? And here, all I did was just went ahead and made this, just took the parentheses out, made this separate. Now on the right side, we're going to do a similar thing. We've got a cosine square of A plus B and a sine square of A plus B. We're going to group those together. So it's cosine square of something plus sine square of the same something. That's going to be 1. That's our Pythagorean identity. So we just group those last two terms. Now we can regroup because of the associative and commutative properties from algebra. Okay. And so let's see what we got. Well, we can take 1 plus 1 is 2 on both sides, and then if we subtract 2 from both sides, the 1 and the 1 are going to disappear there. So that leaves us with 2 sine A sine B minus 2 cosine A cosine B equals minus 2 cosine A plus B. Now, not subtract 2, but yeah, that subtract 2 is what I did from there to there. To go from there to the next step, I'm going to divide both sides by negative 2 to get cosine A plus B by itself. So if I divide by negative 2, that makes this negative 1 and this one positive 1. Now if I just rewrite the order, I get cosine A plus B equals cosine A cosine B, that's times, minus sine of A times sine of B, and that's exactly what we wanted to prove. And so we were able to do our proof. Okay? Notice that it really doesn't matter where this angle is. We can still think of it the same way. Maybe we're not doing the arcs the same way here, but if angle A goes all the way to here, then we have the same setup. So it really doesn't matter where we draw this thing. Okay, so there is a basic cosine angle sum identity. Cosine of A plus B is cosine A times cosine B minus sine A times sine B. You need to memorize this one. This is too difficult to try to derive in the middle of a test situation. So you want to be able to use this without having to derive it on a test. This one was the hardest one to derive. Once we derive this one, we can use it to do some other, to solve some other identities or create some other identities. Before we finish this, let me go on and look at a couple other things with this particular thing. Here is a graphical verification of the same identity. So here is cosine of x plus b, and I can change whatever b is. Okay, so I can basically put in, this puts in lots and lots of values for x and computes the y's. Y equals cosine of x plus b. So basically it's working this out for many values of a with the same specific value of b, which is, right now 0.7. Here's the graph of the other one, and notice it's right on top of it. Cosine of x times cosine of b minus sine of x times sine of b. You can see the two graphs on top of each other here. And this proves that they're the same for that specific value of b and all values of a. And notice if I now take this and put in different values of b, it's just going to shift it left or right, but it turns out, well, we know that's what it does to the red one, but look, it turns out to do the same, has the same effect on the blue graph as well. Very interesting. And so we can see visually that these are the same. Now, if you wanted to do the same thing in your calculator, you can. So let's just kind of look at that verification on the calculator. Okay, and we're going to basically do this the same way. Okay, so if I do it the same way as this, I'm going to store some value in B. So it could be anything. Let's say 7. Store as alpha B. And now go to y equals. Let's clear this out. I've got a stat plot on. Let's turn that off. Let's go to I've got it there. Let's go to mode. Make sure I'm in radians. I am. Okay, everything's good there. Okay, so now I should be able to go to y equals. And if you want to verify an identity, you can put the left side as y1 and the right side as y2, and they should have the same graph and the same table. The only problem is I have two variables, a and b. If I just had one variable, I could let it be x. So the way around it is basically the same thing I did here, is I do cosine of, here I let the a be the x, and I put in that particular one value of b, which was at 7 or something at this point. And then I do the other one, cosine of, I put x for a, so it'll change, and then cosine of b, so that's a specific value of b, minus sine of x times sine of b. Okay, and let's just start with a zoom trig, zoom 7. Now here's one graph. And you know what I could have done is this. Watch this. Let me stop. I stop it here. Let's make this second graph thicker. Okay? So when I see the first graph, it'll graph thin. And if this is right, the second graph will graph right on top of it. And by making it thicker, I can see it trace over. If I just made it thin, I wouldn't be able to see that it was tracing the same graph. If you just do this with the same thickness of graphs, you have a little problem, because when you're looking at here, you're not guaranteed that the second graph could possibly be off the screen. So one way, of course, you can check that is to trace it. And now we're tracing along the y1, but if I hit the up or down arrow, we're tracing along y2, and notice no matter where I go, hitting the up or down arrow does not change the y value, it changes which curve we're on. Probably a better way to look at this is to go to your table, do some sort of auto table going up by whatever amount, and then just look at the table and see that they're the same. I'd probably check some negative and some positive values, check 0, and it looks like they're coming out the same. Now, of course, this only checks it for that specific value of b, but I can now go back and put something else in b, let's say -1, store that in b, and now go back to my table. Of course, that's going to change the table, but it's going to be hopefully still the same for both the different sides. And I could try this for several different b values, and once I've done several of these, I'm fairly convinced that it's correct. It's not a proof. Okay, what do we have to do for the proof? Well, that's why we had to go through all this. This is the actual proof over here, but we can get a reasonable we reasonably feel sure that this is probably going to be an identity by checking at a bunch of points. Okay. Now, of course, there's some conditional equations that are true at infinitely many points. That's true for most trig functions. So if you happen to pick all the points where it's true, that wouldn't guarantee it is an identity. But since we're just sort of randomly picking a bunch of points here, it's a pretty good idea that it's probably going to be an identity. And this version here in the sketch gives us a little bit better indication. Okay, let's do a couple other things here. Now we can use this to find some things like this. What is the cosine of, say, pi over 4 plus pi over 3? Well, according to our identity we just proved, that's cosine of pi over 4 times cosine of pi over 3 minus sine of pi over 4 times sine of pi over 3. Well, these are things that we know. Remember, when we take a pi over 4 for an angle, we can place the special triangle 1, 1, square root of 2. You should memorize that triangle. Okay, and so the cosine of this is 1 over square root of 2, or square root of 2 over 2 if you rationalize the denominator. Okay, and the sine of that angle is also 1 over square root of 2. Okay, now what about pi over 3? Pi over 4 is 45 degrees. Pi over 3 would be 60 degrees. Let's see if I can draw it something like this. No, that's not correct, but okay, this is pi over 3, 60 degrees. This one over up here is 30 degrees, or pi over 6, right angle. And if this side is 1, this is 2, and this one is square root of 3. Again, you need to memorize that special triangle, and then we can look at all the trig functions from this. So the cosine of this angle is 1/2, and the sine of this angle is square root of 3 over 2. Now I probably want to rationalize the denominator, so I'm going to take this first one and multiply by square root of 2 over 2. Square root of 2 over square root of 2, excuse me. And I get square root of 2 over 2. Okay, now let's go over some basic arithmetic here. If you have A over B times C over D, that is A times C over B times D. It's one of the basic things of how we multiply fractions. The other thing is, if you have the square root of A times the square root of B, you get square root of A times B. So we're going to use those properties. So here we're going to multiply the denominators. 2 times 2 is 4. 1 times square root of 2 is square root of 2. Here we're going to multiply the denominators. 2 times 2 is 4. Square root of 2 times square root of 3, we're going to use this property down here, and it's going to be the square root of 2 times 3, or square root of 6. Now let's talk about how we add fractions. If we have a common denominator, A over B plus C over B, that's A plus C over B. We get to keep the same denominator. Okay, basic idea about adding fractions. So we have a common denominator already. We keep that as a 4, and we can do square root of 2 minus square root of 6. And we need to leave it like that, okay? So it is not true, for example, that square root of A plus square root of B, there's nothing really you can do with it. It's not square root of A plus B. It's not, so square root of A minus square root of B is not square root of A minus B. It's not, B minus A and then the opposite. So square root of 2 minus square root of 6, for example, it's not square root of negative 4. It's not negative square root of 4. It's not anything. There's nothing you can do with it. You have to just leave that like that. Okay? It just doesn't work out. Just to show you that, for example, Let's try square root of 4 plus the square root of 25. Okay, we know this is 2, we know this is 5, and that's 7. So we know it actually is 7. But if we did square root of 29, that's definitely not 7. 7 squared is not 29, it's 49. So that's not the same. That's not the same thing. That's the square root of 49, not the square root of 29. So those are completely different different things. So you can't put those together. Okay, so we can work it out and get this for our final answer. Now notice what this allowed us to do was to find an exact value for some other thing. Now what if we were to add these together? This could have started this way, so pi over 4 plus pi over 3. Well, first thing I can do is factor the pi out, and then I'm just adding fractions 1/4 plus 1/3. Okay, so how am I going to add that together? Well, I need to get a common denominator, so I'm going to multiply this one by 3 over 3, and I'm going to multiply the second one by 4 over 4. So this is 3/12, and this is 4/12, still times pi, which is 7/12 pi. So I could have started with cosine of 7 pi over 12, and this allows me to find that. So what would I have to do? I'd have to decompose that 7 pi over 12 into a sum of two things that we know how to do. Well, what do we know how to find exact values for? Well, pi over 6, pi over 4, pi over 3, pi over 4, pi over 2. So those angles, pi over 2, pi over 3, pi over 4, pi over 6, those are special angles that we know how to find the exact trig values of. And so by decomposing 7 pi over 12 into pi over 4 and pi over 3, we're able to make this work. So let's do another one here. So if we have cosine of, let's see, what can I do here? How about 75 degrees? Okay, well, in degrees, the things that we know are, things like, well, we know like 90 degrees, and we know 60 degrees, and 45 degrees, and 30 degrees. Can we make this out of these somehow? Well, look here. If we add those two together, doesn't that work out to be 75? So we could write this as cosine of 45 degrees plus 30 degrees. And now I can use my identity that we just proved. Cosine of 45 degrees times cosine of 30 degrees minus sine of 45 degrees sine of 30 degrees. Again, I'm going to use my same special triangles. 45 degrees here is 1, 1, and square root 2. So cosine 45 degrees is 1 over square root of 2, or square root of 2 over 2, as we've already seen. Sine is also square root of 2 over 2 if it's 45 degrees for the input. Now this time 30 degrees is here for cosine and sine. So there's 30 degrees. This is the short side, so that's 1. Hypotenuse is 2. Longer leg is square root of 3. So the cosine of here is square root of 3 over 2. And the sine is 1/2. So that's the square root of 6 over 4 minus the square root of 2 over 4. And again, they have a common denominator, so I can put them together like this. But I cannot combine the numerator further. Okay? So there's another example of how we can do that. So the key was to break 75 apart somehow into sum or difference of angles that are some of these special angles that we know. So there's an example of how we can use this trig identity that we came up with, cosine A plus B equals cosine A cosine B minus sine A sine B, to find exact values of special angles. Okay? And so in some cases we can use this to expand which angles we can find exact values for. Now, once again, proof was a little bit challenging here, so be sure that you have this particular identity memorized so that you can use it to derive other identities or to evaluate expressions like we did on an exam, and you don't have to go through this proof again. So be sure you memorize this one.